Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element lutetium. I have a little sample of it right here. It's in that vial. It's a little hard to see, so let's go back to the slides because I put it on my scanner and magnified it for you so you could see it a little bit better. Let's actually magnify that a little bit. It's a shiny, silvery metal when kept inside a glass vial away from the oxidizing effects of the atmosphere. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements. I encourage you to pick this up. Check out his fantastic website, periodictable.com. Lutetium is the 71st element in the periodic table. Its atomic number is 71 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Lutetium was independently discovered in 1907 by American chemist Charles James, French scientist Georges Urbain, and Austrian mineralogist Baron Karl Auer von Welsbach. All three chemists worked with the oxide of our previous element ytterbium. That oxide was ytterbia, or ytterbium oxide. They discovered within ytterbia a new element oxide, lutetia, or lutetium oxide. The pure metal was not produced until 1937. Georges Urbain was given credit for the discovery of lutetium, though there were vicious arguments between him and von Welsbach. He called the element lutetium after the Latin name for Paris, though the name was slightly modified in 1909 by the International Union of Pure and Applied Chemistry, the IUPAC. They spelled the element with a T rather than a C, and that's the way we spell it today. Welsbach had named the element Cassiopeium after the constellation Cassiopeia. If you look in the northern sky, you can see Cassiopeia as a W. It's actually the queen in her chair. I like that name much more. Unfortunately, I was not a member of the International Union of Pure and Applied Chemistry in 1909, nor am I a member now. Many rare earths were obtained from an ore discovered in an obscure mine in the town of Ytterby, Sweden. This small city has 4 elements named directly after it: yttrium, terbium, erbium, and ytterbium, all these elements from the Ytterby mine. Not bad for a town with a population a bit over 3,500. Lutetium is also a minor component in these ores. The Ytterby mine has many rare earths, but it isn't big enough to be commercial. One commercial source of rare earth elements is the mineral monazite. Monazite is a phosphate with lanthanum, cerium, praseodymium, and neodymium as major substituting elements, and most of the other rare earths as minor constituents. It's usually found in the form of a sand with other minerals. China, India, Madagascar, and South Africa have large deposits of monazite sands. Another source of rare earths, including lutetium, is the mineral bastnasite, which is a carbonate fluoride with lanthanum, cerium, praseodymium, and yttrium as major substituting elements. Both monazite and bastnasite are mined for many rare earth elements. One last rare earth-containing mineral has the coolest name, xenotime. This is normally a yttrium orthophosphate, but other elements can take the place of the yttrium, including lutetium. Let's take a look at the rare earth content of the previous 3 minerals. You can see from this table, lutetium appears in low percentages, accounting for up to only 0.01% of bastnasite, up to 0.1% of monazite, and 0.4% of xenotime. Even though lutetium oxides occur only in small amounts in bastnasite and monazite, so much of these minerals are processed for other rare earths, These minerals are a major source of this element too. Lutetium belongs to a row of chemical elements known as the rare earth metals, or lanthanides, since lanthanum is the first element in this periodic table row. Lutetium is the 15th and last element of the lanthanide series. Friends, I'll be glad to get back to the transition metals, but it's been an interesting journey through the rare earths. Technically, both scandium and yttrium are also included in the rare earth metals group, since they're both members of the same periodic table column. Both the lanthanide row and the actinide row below it actually fit in the two spaces after barium and radium. But if we displayed the table in this fashion, it becomes too long and unwieldy to fit in books or on posters. This is called the long form of the periodic table. Even though most of the rare earths are not so rare, lutetium ranks as pretty scarce, coming in as the 82nd most abundant element in the universe by mass, actually the third least abundant element on this chart, only 1 part per 10 billion. 10 times as abundant in the Sun, it's the 61st most abundant element at 1 part per billion. It's the 74th most abundant element in meteorites, about 2.9 parts per 100 million. In the crust of the Earth, it's the 60th most common element at 5.7 parts per 10 million. Still, 4 times as common as silver. Lutetium is the 65th most abundant element in the oceans, virtually non-existent at 150 parts per quadrillion. And lastly, and not surprisingly, there is no lutetium in us. As with most elements, the price of lutetium varies widely with purity and the quantity you buy. 99% pure lutetium oxide goes for about $775 per kilogram. The pure metal is about $1,800 per kilogram. It's pretty expensive stuff. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own showing that element's growth over the age of the universe by various processes. Lutetium is here. I understand this looks complicated, but let's look at just lutetium a little closer. The horizontal axis of this square represents time, from the Big Bang to now. The vertical axis shows the proportion of lutetium created by various processes. The majority of lutetium present today is believed to be produced in supernovae, the yellow area. A bit over 1/3 is produced in dying low-mass stars, the magenta area, and a very small amount, that green sliver on the top, is produced in neutron star mergers. Note the lutetium produced by dying low-mass stars, the magenta area, doesn't get started until a bit later in the history of the universe. That's because low-mass stars exhaust their nuclear fuel much more slowly, and they last a long time before they start dying. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 71 protons for lutetium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes and are chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 35 known isotopes of lutetium, and of these 35, there's only one stable non-radioactive isotope, lutetium-175. Lutetium is therefore a monoisotopic element. There are 23 of those, by the way. You would think that the only stable isotope would make up all of the naturally occurring lutetium in the universe, but it only makes up 97.41% of naturally occurring lutetium. What? As we'll see in the next slide, there's also a long-lived radioactive isotope, lutetium-176, that makes up the rest, coming in at 2.59%. That adds up to 100%. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of lutetium occupy the same place in the periodic table. Of the radioactive isotopes of lutetium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest lutetium half-life is lutetium-176, with a half-life of 38.5 billion years. That's almost 3 times the age of the universe. So we shouldn't be surprised to find a bit of this stuff still hanging around, and why it still makes up 2.59% of naturally occurring lutetium. Not enough time has passed for all of it to decay away. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2 and we'll be doing a lot of dividing by 2. If you wait 1 half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait 1 more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's 1 remaining atom after 10 half-lives here. If you waited 1 more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Lutetium is a fairly dense element at 9.841 grams per cubic centimeter. As a reminder, water has a density of 1 gram per cubic centimeter, and I've put up more densities for you here. You can see that lutetium is a little denser than copper at 8.96 grams per cubic centimeter. It's the densest element of the lanthanides. Let's look at the densities of more elements. Here is a graph of the elements from highest density to lowest density. When I do this talk with an actual audience, I have a set of blocks so you can feel density for yourself. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, and magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, lutetium's density is 9.841 grams per cubic centimeter, the magenta circle, midway between copper and lead. Lutetium's melting point is 1,663 degrees Celsius, or 3,025 degrees Fahrenheit. It boils at 3,402 degrees Celsius, or 6,156 degrees Fahrenheit, a whopping 1,739 degrees Celsius above its melting point, 453 degrees above the average distance between melting and boiling points for the elements. One thing I haven't really discussed yet is that all the lanthanides, including lutetium, share a common trait. They all have 2 electrons in their outer shell, like you see here in lutetium. Let's look at the whole group. Here you see all the lanthanides. Notice they all have 2 electrons in their outer shell. Now, chemical reactions are pretty much governed by the electron configuration of the outer electrons. So you might expect that all the lanthanides would be chemically similar, and you'd be correct. They are so chemically similar that they're difficult to separate from each other. Normally, when you proceed up the periodic table, you add electrons to the outer shells. However, in the lanthanides, you might notice that you add electrons to the inner D and F shells rather than to the outer S shell, which is completely full. It can only hold 2 electrons. If we compare the size of the lutetium atom to that of hydrogen, we'd see something like this. The lutetium atom is about 4 times the size of hydrogen. As I just mentioned, all the lanthanides share the property of 2 loosely held outer electrons, and this makes their atoms fairly large. By the way, a picometer is a trillionth of a meter. Atoms are extremely small. Here, our atom size is sorted from largest, cesium, on the top left, to smallest, helium, on the bottom right. Lutetium has the 16th largest size atom of the elements. All the rare earths are fairly large. Let me mark the other lanthanides in blue. Notice how they're all clustered towards the top of the chart. Lutetium is a relatively soft element, coming in at 2.6 on Mohs scale of hardness, a bit harder than silver and gold at 2.5 and a bit softer than aluminum at 2.75. Lutetium does not expand much when you heat it. It has the 50th highest rate of thermal expansion, about 10 parts per million per degree Celsius. This means that if you had a 1 meter long bar of lutetium, we'll magnify this by a factor of 10 just to see it, and you heated the bar by 1 degree Celsius, it would get longer by only 10 millionths of a meter, or about 1/5 of a hair width. Here's the periodic table of the spectra. Lutetium has a complicated set of emission lines, which uniquely identify the element to scientists. No other element gives off these colors when excited. There aren't many unique applications of lutetium that can't be done by the other chemically similar and cheaper lanthanides, but there are a couple interesting and somewhat related uses. In your home, cats are pets, but in medicine there are major differences. A CT or CAT scanner and a PET scanner are 2 different machines, sometimes combined into one like you see here. A CT or CAT scanner sends X-rays through you from many different angles to build an image of what's going on inside your body. A PET scanner looks at radiation emitted from your body after an injection of a radioactive tracer. The PET scan targets specific areas of the body that interact with the tracer. How does that work, and what's lutetium have to do with that? The PET scanner uses a crystalline substance called LYSO, or lutetium yttrium silicate, here seen in its raw manufactured form. A small amount of the element cerium is added to the crystal, also called doping, so technically this is cerium-doped lutetium yttrium silicate. The bulk material is sliced and diced into more usable shapes, usually 3 millimeter squares. The LYSO gives off a very small flash of light when hit by a gamma ray from the injected tracer element. This phenomenon is called scintillation, and the LYSO crystals are therefore called scintillators. The small flash, often a single photon, is detected by very sensitive photodetectors attached to each LYSO crystal. In a PET scanner, as I previously mentioned, the patient is injected with a low dose of a radioactive tracer. A variety of radioisotopes can be used with varying half-lives, depending on what the physician wants to see. The radioisotope is usually attached to a sugar of some type that gathers in the body at the location where higher metabolism is taking place, where the sugar is needed. This could be in the brain or in a tumor. The tracer decays by giving off a positron. This is a positively charged antimatter electron. The positron quickly meets a normal negative charged electron. They mutually annihilate, creating 2 gamma-ray photons which head off in opposite directions. In the PET scanner, the patient is surrounded by a ring of gamma-ray detectors, including the lutetium scintillators, which detect the 2 gamma-ray photons. The process of making a PET scan takes a few steps. First, we need to detect the gammas in our lutetium scintillators. Then, the gamma detectors send their signals to a computer that looks for coincidences of the two gamma rays given off by the electron-positron annihilation. It rejects any single gamma ray which is considered noise. We are only interested in the pairs of gammas. That computer then sends this data to another computer to reconstruct the image of your innards. Amazing technology. Radioactive lutetium-177 looks promising as a treatment for metastatic prostate cancer that's hormone resistant. Prostate tumors overproduce a protein called PSMA, or prostate-specific membrane antigen. This antigen is specifically overproduced in metastatic castration-resistant prostate cancer. Now that's a frightening-sounding form of cancer. A drug called lutetium-177 PSMA 617 specifically targets this protein and latches onto it. Radioactive lutetium-177, with a half-life of about 6.6 days, is attached to the drug. When the lutetium-177 decays by beta particle emission, most of the radiation goes into destroying the tumor, because these betas are limited-range medium-energy electrons. Here, we see a series of PET scans showing the decrease in tumors visible as white spots in the abdomen, neck, and chest over a period of time. This extends the patient's life, but is not a cure. Your body does not use lutetium, but probably still contains a few micrograms or nanograms or femtograms absorbed from the environment. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about lutetium. Helicopter Dad, keeping your electrons close to your nucleus. I think even Mary Soon Lee was running out of things to say about the lanthanides. In the next program in this series, we'll return back up to the main part of the table and begin examining a new row of transition metals I've marked in blue. Here, we'll start our exploration with the element hafnium. I hope you'll join us. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element lutetium.